Here I discuss in particular notations which I will use in this class and compare these with notations that you may have used before and some of the notations which are used in Kundu. So we'll compare notations used in mathematics, the full notations, the notations which I will use in my notes, which also overlap sometimes with the notations in Kundu, and the index notations which are also found in Kundu. And this is important because you always need to be able, when you write a formula, to know what is the nature of the mathematical objects that you are writing, and make sure that you're always adding terms which are of the same sort. And by this I mean, what rank of tensor is the object you're writing. So let's start with the simplest mathematical objects, which are scalars. So these are just numbers, and sometimes you will hear them being called rank 0 tensor. So a scalar is, for instance, going to be your density. It's just a number. The viscosity, but a pressure field is also a scalar. It's just a number. Or a temperature field is also a scalar. So in full notations, that's how you write in mathematics. This is how you would write it also, just exactly the same with full notations. In IFD, of course, scalars are always going to be written as scalars, and in index notation, it's the same. So here, it's very easy. When you see just a symbol written, then it's a scalar. Now, if you go up one rank 1 tensor are vectors. So in mathematics, you may have written them as a letter with an arrow on top. If you're thinking about what does this full object look like, well, a rank 1 tensor is or a vector is a one-dimensional array. So if I had to present, this is how you would typically write velocity. If I had to write the full notation, then there would be 3 components. If it was in 3D, u, v, w. So this is a rank 1 tensor, so a one-dimensional array. In IFD, I will simply write them as a letter with a bar underneath. Those are the notations which I will use. In Kundu, oftentimes you will see, instead of the bar, a bold letter, lowercase bold letter. Usually in IFD, if I'm writing a lowercase with a bar underneath, that means that this quantity here is a vector field. So it's defined at every location. And if I'm using a capital letter with a bar underneath, then it's a single vector. So for example, a capital U could be the velocity of an object. Now, the index notation, you would write a vector simply as a letter with one index. And you're not going to write U1, U2, U3, but you write UI, and it is implicit that the index I goes from 1 to 3. Moving on again, one rank, the next rank are rank 2 tensors, which are matrices. So in mathematics, you may have seen these written as a symbol with 2 arrows. Right? And really what these correspond to are 2-dimensional arrays now. So matrices with 2 dimensions. In IFD, usually matrices I will represent as a letter with 2 bar underneath. And oftentimes in Kundu, the equivalent notation would be a capital bold letter. So if you see a bold letter, which is a capital letter, usually in Kundu, that means a rank 2 tensor. And for index notations, you simply write one letter. You will see that in the Kundu book sometimes. One letter and you write two indices. You don't write the full matrix, but implicitly, because there are two indices, you assume that both I and j can go from 1 to 3, and therefore implicitly this is a notation to represent matrices. All right, so there are a few things which are important to notation, which are important to see. One is the dot product, or maybe you're used to the name inner product. So the dot product of two vectors in mathematical notation you write as A dot B. If you write it in full notation and your vectors have coordinates, so A has coordinates A1, A2, A3, and same for B, then the dot product is equal to A1B1 plus A2B2 plus A3B3, which you can also write as the sum from I equals 1 to 3 of AI BI. In the class notes, I will write this dot product also as a dot with A as A dot B. And in index notation, what you will see is this inner product will be written as AI BI. Here it's important to note that you have two indices and they're repeated, so it's not the same as here. Here we had two different indices, and so whenever you see one repeated index in index notation, that means that the summation is implicit. So if you compare it to the full notations here we did write the summation sign, and here we don't write it, but it's implicit that there is a summation over I. All right, one operation which you will see a lot is the gradient. In mathematics, oftentimes it will be written as grad of some quantity, some field phi. That would be in full notation partial a vector, right, with in each component the partial with respect to the variable. So partial phi partial x, partial phi partial y, and partial phi partial z. In the class, I will use the nabla notation and write the gradient as this. Nabla of phi, if this is the gradient of a scalar field, or for instance nabla of u, if this is the gradient of a vector field. And in index notation we simply write these as partial phi partial xi. Again, you have a single index here, and so it's implicit that I goes from 1 to 3, so this is a vector. You also have the divergence, which in mathematics you may have seen as div of a vector. In full notation, that will correspond to the number partial u partial x plus partial v partial y plus partial w partial z. In the class notes, I will also use the nabla notation, and you write the divergence of u as nabla dot, and it's very important not to forget dot u. This is how we write divergence. And in index notation, you will write it, you will see it in the book sometimes as partial ui, partial xi. Again, here you see you repeated index, so the summation over I is implicit. Here, if my components were u1, u2, u3, I could also write this as the sum of partial ui, partial xi from I equals 1 to 3. So you see that between this notation, the index notation, and the full notation, we omit the summation. Then there is the Laplacian. In mathematics, you may have seen it written as the Laplacian sign, phi. In full notation, that would be equal to the second partial with respect to x of phi plus the second partial of phi with respect to y plus the second partial of phi with respect to z. In the class, the way I will write it, you know that the Laplacian is the divergence of the gradient. So if this is my function, that is here the gradient of the function, and then that would be the divergence of the gradient, and therefore it's the Laplacian. Here you have an inner product, it looks like, between the two nablas. So usually I will write this as nabla squared phi. That would be notation for the Laplacian, and in index notation you would simply represent this as second partial of phi with respect to x. Note that here there are two partials, so there's a partial with respect to x and another partial with respect to x of phi. Those are the same, those represent the same, so you have a double index I, and therefore the summation is implicit again. And now the last operation that we will see is the dyadic product or the outer product. In mathematics, oftentimes it will be represented as a vector with this symbol here, the other vector, or sometimes just with a cross. In full notations, this corresponds to really the vector A times the multiplied by the transpose of the vector B. So you could see it as this product between a column vector and a row vector. And so the rank of this dyadic product is, in the end, you have a matrix. It's a rank 2 tensor. In the class notes, I will simply write a vector A, and then here no cross, no dots, nothing, and directly the vector B. And in index notation, you will see that as AI and B with another index. Okay, so what the notations in IFD allow you to do is to directly, just by looking at the quantity, to know what the rank of tensor it is, just by looking at the bars and the dots. So you always, in any sort of formula, you would go from right to left. And so if you find a bar, this is plus one, this is 1. If between the two symbols there is nothing, so it's a dyadic product, then it is plus, and then you count whatever next bar there is. If you find a dot, then it is a minus. So here, for instance, you find no bar, so the rank of the tensor is 0, and this is a rank 0 tensor. Here you have 1 bar, so this is a 1, and there's nothing else, so this is a ranked 1 tensor. Here you count the bars, you find 2 bars, so this is a rank 2 tensor. Here you have the first example of the dot product, so you have B, you have 1 bar, this is rank 1. Now I find a dot, so that means minus a rank 1, so this is 1 minus 1, 0. And so a dot product is indeed a scalar, and the rank of the dot product is 0. The gradient here, phi, there is no bar, so the rank is 0. There is no dot, so it's a plus a 1. So this here is a rank 1 tensor, and the gradient of a scalar product, of a scalar field, is a rank 1 tensor. It is a vector. Now let's look at the gradient of a vector. I have a 1. Here there is no plus, there is just nothing, so that means there is no dot, so that would be a plus. So I have 1 plus 1. This is a rank 2 tensor. The gradient of a vector is a matrix. Let's look at the divergence. Again, here you have 1 bar, so this is rank 1. I find a dot, so that means minus rank 1. So 1 minus 1 is 0. The divergence of a velocity field is indeed a scalar. It is a number. Here I have a 0. Rank 0. Now I have to be careful of this squared, because this squared is really a 1, again minus a 1, so that remains a rank 0. The Laplacian of a scalar remains a scalar. Let's look at the inner product. I have a bar, this is a 1, I don't have the dots, just have nothing here, so it's a plus 1, so this is rank 2. So you can always know what objects you have by just counting the bars and the dots. And so you should always make sure that you are adding vectors with vectors, matrices with matrices, but you can never add a rank 1 tensor with a rank 2 tensor, for instance. If you're looking into the book of Kundu, you can always know the rank of the tensor by looking at how many indices are not repeated. So if you have no repeated indices, then you add 1. Per non-repeated indices, you add 1. So here for a scalar, there are no indices, so this is rank 0. Here you have 1 non-repeated index, it's just I, so it's rank 1. Here you have 2 non-repeated indexes, so it's rank 2. Here I is repeated, so you have 0 repeated indices. So this is, 0 free indices, so non-repeated indices, so this is rank 0. Here you have 1 non-repeated index, so this is rank 1. Here the I is repeated, so you have 0 non-repeated index, so this is rank 0. Same here, and here this is rank 2 because you have 2 non-repeated indices.